entry is the -1 singleton. Here the leading entry is the 0 singleton. Here the leading entry is the 1 singleton. Those are all different. That's good. How about the condition that the leading multiplicities all be strictly positive? Yes, the leading multiplicities are strictly positive. They are 1 and 1 and 2. What about the last condition, that for each one of these leading entries, the other vectors should have entries which are positive and smaller than that value? Okay, so that's all right for the first entry. The 1 has some zeros elsewhere. If we look at the second, the leading entry, which is a 1 there, and we look at the other vectors, we see that this one does not have an entry in that position in the allowed range. Okay, so we want this one to be changed so that it's between 0 and 1. Including 0, but not up to 1. So well, then we'll have to multiply, we'll have to add a multiple of this one to this one. So let's do that. Let's take row 4, and I'm going to add 2 times row 1 to it. Okay, so this one here plus 2 times this one. So I'm going to get 1, 0. This one plus 2 times that one gives us 4. And this one plus 2 times that one. This one plus 2 times that one is -7. And we keep that a new name, same with 7. And we get rid of 4. So now we're in a situation where we look in the second column, number 2, number 6, and number 7 on the remaining one, that the entries are 1, 0, and 0. That's all good. What about the last leading entry, though? This 2 is this vector here. So we would want the other entries in the third column to be less than 2. So this one is not less than 2, and neither is this one. So we're going to have to subtract multiples of these ones to get that same range. So I'm going to take number 1, and I'm going to just subtract 6. Just subtract 2, and that's 0, 1, 0 minus 2. I have to underline these positions, and that'll be number 8. And that's got rid of, sorry, that was not number 2, that's not number 1, that was number 2 that I did that to, wasn't it? I took that one there, and I subtracted this one. So number 2 is now history. Then we're left with 6, 7, 8. And we have to do the same kind of thing with 7. So we'll take 7, and we'll subtract 2 times row 6. So we'll subtract 2 times 2 to give us a 1, 0, 0, minus 7. And this one is now gone. So, the neat normal form is H is going to be the MZ consisting of, I'll write it out in terms of the decimals. So I'll start with this one here. 1, 0, 0, minus 7. 0 underneath it. And then this one here, I need 0, 1, 0, minus 2. And then this one here, which is 0, 0, 2, 0. End of the expression. So if I've done that right, I hope my arithmetic was correct. Now we see that this is in Hermite normal form, and the leading entries are all different. The other entries in the columns of those leading entries are, well, in this case they're 0. They don't have to be 0, but they could, but they have to be positive and less than whatever the leading multiplicity is. And as for the other things, the things that are in the other columns that are not associated to leading entries, we don't care about them. Okay, so this one is in the Hermite normal form. So that's how it works. In our next video, we're going to talk about lattices and their relationships using the power of this Hermite normal form. I'll just join you for that. I'm Noah Walberger. Thanks for listening. So there you go, Noah Walberger. In this video, we're carrying on discussing bases and dimensions for integral linear spaces. And we will once again at this interesting and important question of given integral linear space, in other words, integer span, we go about finding a good basis for that space. So a remind you the setup is that we're starting with a bunch of M sets and we're taking linear combinations of M sets. That's all what an integral linear space is. And it's very general. You just have a bunch of M sets, 1, 2, 3, 0, 17, and you just allow to take all possible linear combinations, in other words, sums of M sets with integral coefficients. And that's the integral span of that gap. And basis for that, I remind you, is another M set of M sets that spans this ring, which also has the property that its linear combinations give us the same object, but which is minimal with respect to the number of elements it has. So of all the we're interested in finding those sets which are minimal at the smallest size. And that smallest size is then the dimension of the integral linear space. So typically a integral linear space has many different bases, and so it's an interesting sort of computational question of trying to find some convenient ones. And I remind you that our geometrical interpretation, so how we should think about these things geometrically, well, we don't have to, is in terms of lattices in space. So, for example, the simplest equilibrium space is just the empty set itself. That's all. If you just count the empty set itself, then all possible combinations of that just give you the empty set, so you never get anything more. There's just one object that's a zero-dimensional kind of equilibrium space. And then if we go up one dimension, where we just have a single, or maybe we have more sets, but they're all sort of essentially multiples of one single set, then we get some one-dimensional situation that we can picture like this, where, say, that's the origin, and here are various m sets. That's an m set. There's 2 times it, there's 3 times it, 4 times it, 5 times it, minus 1 times it, minus 2 times it, and so on. Okay, so it's essentially like a copy of the will be vexels. Let me remind you that a vexel is an m set of singletons. A singleton is a integer contained in square brackets, so it's a list with one element, or you can't really tell it apart from an m set with one element. So these are all singletons. And so a vexel consists of something like this. So inside here, there's a vexel because it's an m set consisting of a bunch of singletons. Actually, it's an integral vexel because you see this singleton 2 here actually occurs as an anti, so it's the anti of singleton 2. What you think about that is the singleton 2 is occurring with multiplicity minus 1 in this integral m set. So when I say m set here, I'm really working in the language of integral m set. Everything is in the integral framework here, even though I don't necessarily say so. Here's another vexel. It's an m set of singletons. Here's another vexel, an m set of singletons. There's another anti-singleton. And instead of writing this, which is a little bit onerous, perhaps, I want to connect that with the more usual notation, and we can do that by using the convention that we talked about last time. So this vexel here, we can write this as 3, 0, minus 1, referring to the fact that there are 3 zeros, 0 1s, and minus 1 2s. And notice that the little bar underneath 3, that's telling us that's the 0 index, that's the number of 0 singletons. Because strictly speaking, we could have even singletons with negative entries inside here, so we could be anywhere on the integral line, really. Okay, so this one here, for example, is 0, 0 singletons, 0, 1 singleton, 0, 2 singletons, and 2, 3 singletons. And here we have 0, 0 singletons, minus 1, 1 singleton, and 2, 2 singletons. And so this m set of vexels could also be represented in this way. This is an alternate way of representing this. And I also want to recall the convention that if a 0 singleton does not appear, in other words, if there's a 0 multiplicity of a 0 singleton, so something like 0, 4, 1, then we'll allow ourselves to rewrite that as 4, 1. So if we just have 1 singletons and 2 singletons and 3 singletons, we'll think about that as like a traditional vector. And so there's a traditional vector, which is really short form for this, and this is really short form for the m set of singletons. Okay, so we're often going to be looking at examples in this sort of world where the actual m sets that we're taking linear combinations of are vexels. This is convenient. It links very directly to linear algebra, and it's actually not really a big loss of generality. So although technically speaking we're actually working in a much broader domain, it's not too hard to see that this approach approach is, well, not completely general, it still captures a lot of the essence of more general situations. Let me explain why. All right, so let's illustrate. So here's a more general M set of M sets. So the big M set is M, and inside you can see three M sets. There's one, and there's another one there. And the ingredients in the M sets are themselves various data structures of different kinds. Because, in principle, we can have any kind of object in our M sets as long as they're already priorly established objects that we understand completely. Okay, so there are no flying spaghetti monsters. There are no infinite objects that we've only waffly described. There are no things like the set of all prime factors of Z. The things that we have in our M sets are bona fide objects. You can write them all down completely, explicitly, and show somebody. Look, that's what I'm talking about. There. All the elements are there. You can check one by one. That's what we talk about. Okay, so let's look at this particular example. We see here, what is this? It's like a set or an ordered set. It's got a comma, so it's an ordered set. Here's a multi-set. Here's a set. There's another copy of that thing. There's the same thing, but an anti of it. There's a singleton. Okay, so we have a number of different objects there. Now, suppose that we were interested in working in the integer span of this particular M set. So we're going to take linear combinations of this M set, and this M set. So if we were going to do this a lot, we might get tired of writing out all these rather onerous elements. And you can match other examples where these things are much bigger and even more onerous. So let's set graph. A4 also, with this prior convention or dictionary that we've established that's over on the side. Okay, but this probably for humans is simpler to work with. If we had to do a lot of linear combinations, we prefer to work with this rather than this. But notice that this is really effectively very much the same as working with this. Okay, what are we doing here? I'm just replacing the A1 with the singleton 1. The A2 with the singleton 2, the A3 with the singleton 3, the A3 with the singleton 3. So the A3 that we've introduced as a symbol is playing the same role as, say, the singleton 3. So when you think about the singleton 3 as being some kind of rather flexible object that might stand for something that we have a dictionary for. We don't have to, but if we have some more complicated situation, we can transfer it to a discussion of an M set of M sets like this, and in that case we're really talking about vectors, because that's now a vector, that's a vector, and that's a vector. So that's why this discussion where we're just using examples coming from vectors is really not so far from being the general case, because we can interpret these singletons as being labels for perhaps some other objects if we want to. Okay, so let's start with an example. Suppose we want to describe the integral linear span of u, v, and w, where u, v, and w are the vectors 4, 4, 6, 3, and minus 8, 1. So we're writing things in terms of vector notation, so that'll be kind of familiar if you're from a linear algebra background, but I remind you that this is just a short form, okay, for a vexel. Okay, for a vexel that has 6 singleton 1s and 3 singleton 2s. Okay, and here is a standard picture of the plane, x-axis, y-axis. The vector 4, 4 would be over 4 over here, 4 over there, that would be that point there. 6, 3 would be over here, that one there, I guess. Minus 8, 1, it's often haste over there somewhere. So this integral linear span turns out to look like this. Okay, it looks like all these red points here. So these are all the points that can be expressed as an integral linear combination of these three vectors or vectors. And we're interested in trying to find a good basis for this. Okay, so I'm going to explain to you a procedure. It's really an algorithm that starts with these three vectors, or vectors as the input, and then there's this procedure that we can do that has reasonably well-described rules and allowed movements, and then we're going to move towards replacing these three with, in this case, two other ones. It turns out that 2, 2 and 0, 3 is the output of this algorithm that I'm going to show you. And what we're going to be able to deduce from that is that the vector 2, 2, which is this one here, and the vector 0, 3, which we can see are vectors in this bilinear span, that they actually form a basis for it. So it's kind of obvious geometrically here that these two vectors are a basis for this, but you can get to any one of these red points by taking some integral combination of this first one, followed by adding some integral combination of that second one.